Placing capacitors across the secondary windings of a transformer can have several potential effects. Firstly, capacitive current. The capacitors will draw a leading current, which can increase the load in the transformer. This increased current can lead to overheating and reduce transformer efficiency. Secondly, resonance. If the capacitance and inductance of the transformer windings form a resonant circuit, it can amplify certain frequencies of noise. This resonance can worsen the noise issue rather than improve it. Thirdly, inrush current. When the transformer is energized, the capacitors will discharge through the windings, causing a surge of current. This inrush current can be several times higher than the normal operating current and can stress the transformer components. Fourthly, ground fault currents. If there is a ground fault on the secondary side, the capacitors can provide a path for high fault currents. This can trip the circuit breaker or cause other safety hazards. Fifthly, harmonic distortion. The capacitors can introduce harmonic distortion into the power line, which can interfere with other devices connected to the system. Other concerns involve capacitor type. It's important to use capacitors specifically designed for power line filtering. Another concern is capacitor voltage rating. The capacitors must have a voltage rating that is higher than the maximum voltage on the secondary windings. Also, capacitor losses. The capacitors will have some internal losses that can reduce the efficiency of the system. Given these potential issues, it's generally not recommended to install capacitors across the secondary windings of a transformer without proper engineering and analysis. If noise filtering is necessary, consider using other methods, such as EMI/RFI filters. Install a commercial EMI/RFI filter between the UPS and the transformer. Use an isolation transformer with an electrostatic shield to reduce common mode noise. Consider noise suppression capacitors. Use capacitors across the input or output terminals of the UPS to suppress noise at the source. In the specific case, the 30 to 60 microfarad capacitors may have helped reduce the noise, but it's important to monitor the transformer and circuit closely for any potential issues mentioned above. Capacitive current increases the load on the transformer, leading to potential overheating and reduced efficiency. Resonance between capacitance and transformer inductance can amplify noise frequencies, worsening the issue. Inrush current from capacitor discharge during energization can stress transformer components. Ground fault currents can flow through capacitors, potentially tripping breakers. Harmonic distortion introduced by capacitors can interfere with other devices. It is crucial to use power line filtering capacitors with appropriate voltage ratings. Internal losses in capacitors can reduce overall system efficiency. Alternative methods for noise filtering include using commercial EMI/RFI filters between the UPS and transformer. An isolation transformer with an electrostatic shield reduces common mode noise. Noise suppression capacitors at the UPS input or output can mitigate noise at the source. Closely monitor the transformer and circuit for potential issues when using capacitors for noise reduction. When selecting capacitors, the voltage rating must exceed the maximum voltage on the secondary windings. Consider the potential for resonance between the capacitance and inductance, which could amplify noise. Inrush current caused by capacitor discharge can be managed with proper design. Ground fault protection is essential to mitigate hazards from capacitor-related fault currents. Harmonic distortion can be addressed with appropriate filtering techniques. It is recommended to consult with a qualified engineer before implementing capacitor-based noise filtering. Ensure that capacitors are properly sized and installed according to manufacturer specifications. Regular inspections and maintenance can help prevent potential problems. Capacitive current is calculated based on the capacitance and voltage. Resonance frequency depends on both capacitance and inductance values. Inrush current magnitude is influenced by the capacitor size and source impedance. Ground fault current levels are determined by the system grounding configuration. Harmonic distortion is quantified using total harmonic distortion measurements. Capacitive voltage rating is typically specified in volts direct current or volts alternating current. Capacitor losses are usually expressed as dissipation factor or equivalent series resistance. EMI/RFI filters attenuate unwanted frequencies using inductors and capacitors. Electrostatic shields reduce capacitive coupling between transformer windings. Noise suppression capacitors are often used in conjunction with other filtering techniques. Monitoring transformer temperature is crucial for detecting overheating issues. Circuit breakers provide overcurrent protection to prevent damage from fault currents. System grounding practices play a vital role in minimizing ground fault risks. Regular power quality audits can identify potential harmonic distortion problems. Selection of appropriate capacitors is essential for reliable system operation. Careful installation and maintenance are crucial for preventing equipment failures. When troubleshooting noise problems, it is important to consider all potential sources. A systematic approach can help identify and resolve the root cause of the issue. In some cases, a combination of filtering techniques may be necessary to achieve optimal results. Consider the impact of any changes on the overall system performance. Always follow applicable electrical codes and safety standards. Consulting with a qualified electrician is recommended for complex installations. Proper documentation of all modifications is essential for future reference. Regular testing and verification can ensure that the system is operating as intended. Investing in high-quality components can improve system reliability. A proactive approach to maintenance can prevent costly downtime. Stay informed about the latest advancements in power quality technology. Consider the environmental impact of any electrical installations. Promote energy efficiency to reduce overall operating costs. Work with qualified professionals to ensure safe and reliable operation. Regularly review and update system documentation as needed. Implement a comprehensive maintenance program to prevent failures. Consider the long-term costs and benefits of any modifications. Prioritize safety in all electrical work. Use appropriate personal protective equipment when working with electrical equipment. Follow lockout/tagout procedures to prevent accidental energization. Ensure that all wiring is properly insulated and protected. Inspect electrical equipment regularly for signs of wear or damage. Replace any damaged components promptly. Keep electrical panels clean and free of obstructions. Use properly sized conductors and overcurrent protection devices. Avoid overloading circuits. Use ground fault circuit interrupters in wet locations. Train personnel on proper electrical safety procedures. Post warning signs in areas with electrical hazards. Keep a first aid kit readily available. Know the location of emergency shutoff switches. Develop an emergency response plan. Regularly review and update the emergency response plan. Conduct drills to ensure that personnel are familiar with the plan. Invest in training to improve personnel skills. Stay up to date on the latest industry standards. Participate in continuing education opportunities. Network with other professionals in the field. Share knowledge and experiences to improve overall understanding. Contribute to the development of new technologies. Support research and development efforts. Promote innovation in the electrical industry. Advocate for safe and reliable electrical systems. Consider the social impact of electrical engineering decisions. Promote sustainable practices to protect the environment. Work to improve the quality of life for all people. Uphold the highest ethical standards in all professional activities. Maintain confidentiality of sensitive information. Avoid conflicts of interest. Act with integrity and honesty. Treat others with respect. Promote diversity and inclusion in the workplace. Encourage open communication and collaboration. Foster a positive and supportive work environment. Strive for excellence in all endeavors. Continuously seek to improve performance. Embrace lifelong learning. Be a responsible and ethical professional. Contribute to the advancement of society. The impact of the 30 to 60 microfarad capacitors could have on the transformer's lifespan and performance. It is not advisable to implement capacitor banks for filtering without first consulting with a qualified electrical engineer. The capacitors, if not correctly sized, may be in fact the root cause of other types of issues in the power signals. Power quality analyzers can be very helpful in revealing and understanding any kinds of hidden problems. These should only be used by qualified technicians. The size and location of a transformer can dictate what is possible in terms of filtering and noise mitigation. Some sites are simply more prone to noise issues than others. Different types of equipment will also be more susceptible to noise. Medical equipment, for example, can be extremely sensitive. Broadcast and production studios would be also on the higher end of sensitivity. There are safety risks from incorrectly installed components, particularly with power transmission equipment. It is best to have an expert evaluate the equipment, the local power grid, and the site before attempting some solutions. These experts will be able to model the changes and predict their effectiveness. There are also some types of equipment that are inherently noisy or unstable. Powerline communication transceivers can introduce many different kinds of signal noise into the environment. If the capacitors are shunting noise to ground, the grounding quality becomes extremely important. It may also be useful to perform a ground impedance test to see how well the grounding system is performing. This can often be a source of noise injection. Radio antennae nearby can introduce noise into the grid through induction effects. In general, it's important to start with the simplest solutions first. Check the grounding. Look for loose connections, measure voltage drops across connections. These are basic and essential troubleshooting steps. The next step is to disconnect suspect equipment and see if the noise goes away. If the noise goes away, it can then be determined whether that equipment can be repaired or if it needs to be filtered. The capacitors might be a temporary fix, but it is more important to determine the root cause of the noise. The root cause could even be something simple such as fluorescent lighting, or other sources of electrical noise. If sensitive equipment is involved, a power conditioner might be a better approach than capacitors. Power conditioners can regulate voltage and also filter noise. The best method to solve electrical problems is to methodically isolate the problem, check the grounding, and then filter as necessary. There are even devices that can inject noise into the power lines. Switching power supplies are a major source of noise. These are common in computers, monitors, and other electronic equipment. Also, consider that the noise may not even be coming from inside the building. The noise could be coming from outside the building and the power grid. This requires contacting the utility company. The utility company will need to analyze the power to determine if there is noise coming from their equipment. The capacitors are also only a good solution if the noise is within a particular frequency range. If the noise is outside of that frequency range, the capacitors will be ineffective. Also, keep in mind that capacitors can fail. If a capacitor fails, it could cause a short circuit. The capacitors will need to be replaced periodically. Consider the cost of replacing the capacitors when evaluating this solution. It is possible that the money saved on the initial purchase of the capacitors will be offset by the cost of replacing them. Also, consider the labor cost of replacing the capacitors. Be sure to document the changes you make to the electrical system. This documentation will be helpful for troubleshooting problems in the future. The documentation should include the size and type of capacitors that were installed, as well as the date they were installed. The documentation should also include a description of the problem that was being addressed. The noise may also be intermittent. If the noise is intermittent, it may be difficult to troubleshoot. In this case, it may be helpful to use a data logger to record the noise levels over time. The data logger can help to identify patterns in the noise. The data logger can also help to identify the source of the noise. Do not make changes to the electrical system without consulting with a qualified electrician. It is important to consult with an electrician before making any changes to the electrical system. The electrician can help you to determine the best solution for your problem. The electrician can also ensure that the changes are made safely. This is important for the safety of yourself and others. The electrical system can be dangerous if not handled properly. It is important to take precautions when working with electrical equipment. Wear appropriate safety gear such as gloves and eye protection. Disconnect the power before working on any electrical equipment. If you are not comfortable working on electrical equipment, call a qualified electrician. Do not attempt to repair electrical equipment yourself if you are not qualified. Electrical equipment can be dangerous if not repaired properly. It is important to have electrical equipment repaired by a qualified technician. This will ensure that the equipment is repaired safely and correctly. The capacitors on the secondary can work, but the problems they can cause could lead to bigger issues than the noise.